All right, so we've gone over index storage, and this is great if you want to draw the mesh or you just want to store the mesh. But as soon as we start to do queries on the mesh, we're going to run into some trouble. So as soon as we start to look up some specific relationships, this is going to fall a little bit short. So let me show you an example. So for example, if I wanted to say, all right, given a particular face, what's the face on the other side of an edge? So remember, in a manifold mesh, an edge can have up to 2 faces. So if I picked out this face 1 and then I picked out this edge here, right here, then 2 would be the face on the other side, right? Now, unfortunately, if I wanted to do this in this format, I would actually have to loop through every single face. Now, there's only 3 here, so that's not too bad. But in Homer, there was like 40,000. So I'd have to loop through all those 40,000 faces until I found a face that had the 2 vertices on that edge. So I'd be looking here for the vertices 1, 3. Have to loop through all the faces. So this would actually take big O of F time, which is really big O of V time. I'll say F just to make it clear. We have to loop through all the faces. And that's a little bit absurd given that there's actually only one face that I'm looking for, right? That's a real needle in a haystack, and I'm going through the whole darn haystack there, right? Okay. Another operation I might want to be able to do, so for this one, maybe I'll draw a slightly more exciting mesh. So let me draw a mesh where I have a few more triangles. So let me do it like this. And so it might be nice for me to query a particular vertex and ask which vertices are connected to it. So it's a discrete notion of what I would call a neighborhood. And so, for example, if I asked you, okay, what are the neighbors of this vertex here? So maybe I'll highlight that vertex in red. So what are the neighbors of that? Well, it would be these 6 vertices in, I guess I'll color them in blue. So let me just do that real quick. All right, so there we go. So given the red query vertex, I would want to say what are, so I'd say vertex dot get neighbors. And again, I'm actually going to have to go through all the faces, right? This time I would, go through all faces until I find one with vertex on it. And add, at that point I'll add the other 2 vertices. So, again, I'm going to go through the huge mesh to find a few. Actually, how many are there going to be? We can kind of approximate that. So if I look at, as I was shown before, there are about 3 times as many edges as vertices. So I'd say there are 3 times as many edges as vertices. Actually, though, each edge double counts the vertices, right? So if I think of the neighbor relationships here, each edge actually contributes 2 neighbors, right? So this edge right here, it says this blue vertex is the neighbor of the red one. The red one is also a neighbor of the blue vertex. So we would actually say that on average, there are 6 neighbors. And if I look back at Homer, I can kind of convince myself that that's true. So I look at this vertex, okay, this one has 5 neighbors. No, 6. No, this one has 6. This one has 5. Some of them have fewer. Some of them have more. This one has 7. But actually, they will average out to about 6. And so it's kind of absurd to have to go through, in this case, it would be, 10,000 faces just to get to 6 numbers in the end. So that's very wasteful in terms of computation. So we're going to have to do a little bit of a space-time trade-off if we want to do better. Okay, so if we want to do that, we can store a lot more information. And let me do my first try at that. So I'm going to create what I call the bloated data structure. This is actually what our library ggslac uses by default. but I'm going to have you code up a better one, which I'll explain in a second. But let's just get started here. And so what I'll do, I'm still going to store the x, y's, and z position of the vertex. But now, I might cheat a little bit. I might say, okay, I know I want to be able to get all the neighbors quickly. So maybe what I'll do is I'll store an array of all the edges coming out of it. So like storing all the spokes that come out of it. And I could also store an array of the faces that come out of it. But I could get those from the edges, right? I could just look up the edges and get the faces. So I can save a little bit of memory there. Okay, and now as far as an edge goes, I guess I have to store the vertices, right? So I guess I'll say v1 and v2, right? So the two vertices that make it up. And then I also have to store the faces. Now one of them might be null if this happens to be on a boundary, right? So this edge here only has one face. On the other side, it's actually got nothing. It's a boundary, but I still have to store 2 pointers. So I'll store a reference, to one face and another face. And then for the faces, I will store all the vertices that are involved. So if we're saying triangle here, that'll just be 3. And I will also store the edges that are on it, E1, E2, E3. All right. So certainly I can do this neighborhood query, the vertex get neighbors very quickly. I just, jump to the vertex, loop through the list of edges. For each edge, just give me back the vertex that is not the one that I queried it with, right? So now I can do this in time proportional, we would say output sensitive time proportional to the number of vertices. Because I store this information directly about which edges are there, I can look up very quickly what the neighbors are. If I want to get the face on the other side of a particular edge, and so if I wanted to, giving you a face and an edge, get the face that's across it. So like I gave you this edge and this face, and I wanted to return this face. Well, I just go to the edge, and I return the face that's not the one you're looking at, the other one, the one on the other side. Also, this is now definitely a constant time operation. So this is a constant time operation. This would be, on average, a constant time one, right? On average, there's 6 of these. And I can at least say it'll be output sensitive. Okay, so how bad is this? Okay, so remember, so this is, so on average, there are 6 of these, right? So each vertex is going to have to store 9 pieces of information on average. So I would say this one accounts for 9V memory. Each edge is going to have to store 4 pieces of information, but remember, there are actually 3 times as many edges as vertices. So I would say this is 4 times 3V, which is 12V, right? So there are 3 times as many edges as vertices, 4 pieces of information for each edge. And then for the faces, I would have 6 pieces of information, right? But then there's twice as many faces as vertices, so that would be 12. And so all together, this is going to be 24 plus 9, which turns out to be 33V. Okay. And sometimes when people introduce this, they will also throw in an array of the attached faces here, which would be, I guess you would say 5 on average if there were 6 edges coming out. So here I've got 1, 2, 3, 4, 5, 6. I guess, sorry, 6 faces. 1, 2, 3, 4, 5, 6. 6 faces coming out on average too. So you might actually add an additional 6 and bring this all the way up to 39. But anyway, this is much worse, right? 9V was what we needed for off, and now we need 33V here. But just to show you, this is what ggslac uses. So if I go to my code base here, this is how I end up initializing all the meshes. So if I go to geometry, I guess I called it basic mesh. I didn't want to make it sound so bad, so I called it basic mesh instead of bloated mesh. But yes, it's a basic, overly redundant mesh class, which kind of puts vertices, edges, and faces on the same footing. So the vertex stores position, x, y, z, a couple other things which we'll talk about later, but yeah, mainly the position and then all the edges coming out of it. And if, as I said, I can look up the faces from that by just going through the edges and adding them to a set of, I'll put both faces on the edge, add them to a set, make sure I don't double count them. Edge, like I said, stores two vertices, two faces. And then, what did I miss here? So I have my edge, and then I must have skipped the face. Okay, yeah, the face just stores the edges. Oh yeah, well, I guess, yeah, I could get away without storing. I guess I didn't store the vertices explicitly here, because I could get the vertices from the edges. Okay, fine. But it turns out that there is a better data structure I can use that's actually a little bit more elegant. It'll use actually kind of a similar amount of space, but it turns out to be a lot easier to maintain, actually. And it's a little bit less obvious. But it'll also give us very efficient algorithms for face across edge and vertex get neighbors. So this is what we call the half edge data structure. And in some ways, this is the gold standard for mesh editing. So we saw off is fine if we're just trying to do mesh storage, but for general mesh editing of manifold, I should say here, it's important that these are of manifold meshes. Okay, so if you have a manifold mesh and you want to start doing surgery on it, or you want to start doing queries on it, the half-edge data structure is great. Okay, so what I'm going to do is, once again, have three tables. One for edges, one for vertices, one for faces. But actually, I'm going to call them H-edge for half-edge and H-vertex, H-face for half-edge. Vertex and half-edge face. Now, why am I calling this a half-edge? What is that all about? Or a hedge? So what I'm going to do, actually, is for each edge, I'm going to have two of these half-edge objects. I'm really going to think about splitting this into two pieces. And so there's going to be one on each side of this edge. And so remember, I told you this is going to be on manifold meshes. So if we think about the order that we go around the vertices in a face, that is going to be counterclockwise order with respect to the normal of that face. And if these are consistently oriented, then that same orientation on the other side goes like this. And if I look at the order that visits the same edge, so here I go through the edge from tail to tip here. On the other side, I actually start over here and go from tail to tip here. That goes in the opposite direction, right? So these half edges are paired to each other across one of the actual edges of the mesh, and they go in opposite directions with respect to that edge, right? And again, that's because they are oriented. So let me go ahead here and straighten this out. And let me add a little arrow here, and I'm going to call this pair. Okay, so each half edge, so maybe I'll start with this. This is my half edge H, is what I'll call it. And H has a pointer to the half edge on the other side. So I'm going to call this H dot pair. All right. So that's the one on the other side. Okay, so each half edge has a pair. Each half edge also has a pointer to the next half edge in counterclockwise order. So this would be, I would call this H dot next. So we also have a pointer to the next half edge in counterclockwise order on this face. All right, so we've got the pair, and then we've got next. Now, in the assignment that I'm going to have you do dealing with this, I also store a pointer to the previous. I'll go ahead and do that here, but some people don't do that because it saves memory. And you can always get to the previous just by going next until you get to the edge right before where you were. But just to point it out here, I'll say, all right, yeah, I've got a pointer to my next, but I'm also going to put a pointer to the previous. It's a space-time trade-off. I'm going to have it there for convenience. But just know that not everyone does this. So here is my previous pointer. And, okay, so I'm going to say that's h.prev. So I'll put it in there. So that's the pointer, another half edge. But also, I'm going to store a pointer to the vertex that's at the tip of this half edge. So maybe, let me draw this half edge a special color here. I guess I'll draw this one in red or something, because that's the one I'm looking at. All right, so it's got its next, it's got its previous, it's got its pair. I'm also going to store this vertex, which I'll call the tip of this half edge. So that would be h vertex tip. And I'm also going to store a pointer to the face that's to the left. So this is a pointer to the face. And because I'm walking around this counterclockwise, it should be totally unambiguous which of the two possible faces that is. Because if I'm walking counterclockwise, well, the face to the left of me is always going to be this one, right, in this picture. So I'm walking counterclockwise, and then the face to the left, that's the face that we say that belongs to this half edge, or that this half edge belongs to. Right? So I'll just say this is, face to the left. Okay. So that's what we need to store for a half edge. That was a lot of information. But notice constant amount of storage. We don't have any arrays here. Okay. Now for the vertex, it's pretty simple. I'm just going to store the x, y, z position again. But I'm also going to store just one half edge that has this as a tail. So I'll say edge h. And so this is an arbitrary half edge coming out of this vertex. So for example, if I were to pick this vertex here, well, let's see, let me find a more exciting one. If I were to pick this vertex here, there's a half edge here that's coming out of it, but there's also a half edge here that's coming out of it. And there's also, and in fact, this red half edge is a half edge that's coming out of that vertex. So I just arbitrarily pick one of the half edges that's coming out of it, and I store that. Okay. And for the face, I actually just store one of the half edges that belongs to it, also arbitrarily. So arbitrary half edge that belongs to this face. All right. So, all right, before I go any further, let me ask the question, how much information is being stored here? How much space does this take up with respect to the number of vertices? Well, I can see that my half edge has to store, with the choice I made doing both next and previous, I'm storing 5 pieces of information. Okay? But I actually have, okay, that's 5 pieces of information, but times 2 times the number of edges, right? Because I split each edge in 2. And then I also remember that there are actually 3 times as many vertices as edges on average. So okay, this is actually pretty heavy. So this alone is going to be 6 times 5 the number of vertices. So this is alone is already taking me actually up to 30V. But I could cut down on that if I So maybe what I'll do is I'll be a little bit disingenuous here and say, well, what if I just got rid of the previous? I don't necessarily need that. So then that's just 4 pieces of information there. Okay, so 4 times, so I'll count it that way. So 4 times 6, so that ends up being 24V. All right. We're going to use this in the assignment, but just for now, if I was trying to save space, I could do that. H vertex, okay, that's going to be 4 pieces of information, right? X, Y, Z, and then one of the half edges. And then face, that's going to be just 1 piece of information, but there are about 2 faces for vertex. So if I look at this, okay, and if I don't use the previous edge, I can actually do a little bit better with memory than I did here. Now I'm only using 30V. I guess here though we saw we could do a little better if we didn't have to store the edges. So maybe it's about a tie with memory. But this one is just, it's going to be a little bit more elegant to do certain surgery on. So we're going to roll with this one. Okay, it's less obvious, and maybe it's about a tie with memory. But let's roll with it, okay? So, but I'll go back and I'll use this again. And so now what I want to figure out is okay, how do I do these operations? So I have to, it's going to be a little bit less obvious than it was in the bloated data structure where I could kind of just look this stuff up directly. It's going to be a little bit less obvious how to do these, but we're going to see that these can be done in output sensitive time still. We're just going to have to be a little bit more creative. So if I were to give you a face and I wanted to know what is the edge on the other side of that face. Okay, so yeah, I guess I would give you a face and I would give you a half edge. Well, then this is trivial, actually. All I have to do is say, all right, so let's say I gave you this face F face here and this half edge H. So then I just have to say, okay, let me go to the other side. I can always go to the other side by saying H.pair. And then I'm going to get the face that's on the left of that, right? So that would be this face. So I'm going counterclockwise order here. The face that's on the left is the other face that I'm looking for. So this one's pretty simple. I just say H.pair face. All right. Getting the vertex neighbors though is a little bit trickier. Okay, this mesh here has gotten a little bit busy. Let me pull down this one here. So I know, okay, so I'll pull down this one. And maybe just for the sake of illustration, I'll get rid of one of these edges here. So this is actually not a neighbor anymore. So let me make that black again. And okay, so let's say that I wanted the neighbors of this vertex, right? And so what I can start with here is some arbitrary half edge coming out of the vertex. So let me just pick one. Let me say that it was this half edge, all right? So we'll say this is the one that it starts with. So I'll call it vertex V, and this is V.H, all right? So this is some arbitrary half edge coming out of this. And so I had to think, okay, well, how do I get to the other vertices that are coming out of this? And, well, okay, so first of all, I mean, I kind of have the first one, right? This vertex here would be just the vertex that's at the tip of this half edge, right? So I would say V.H.tip, right? So I got that one. So this is V.H.tip. But how would I get to like this one? Well, I guess I could go next, right? So I could say V.H.next. That would be the next one in counterclockwise order. So I could say V.H.next.tip. That would get me there. But then how do I get to this one? If I keep going next, well, I'm kind of stuck. I'll just keep cycling around this one face. So it turns out what I have to do, I actually have to move to the next face over here. I have to do like what I had done before when I flipped to the other face on the other side. So what I have to do is actually flip to the other side here and say, okay, this is going to be V.H.pair, right? So this is V.H.pair. And okay, now I can do next. All right, so this is V.H.pair. And if I go V.H.pair.next, I actually do get a half edge that has a neighbor at the tip. So I'm looking for a half edge whose tail is my query vertex V. And so if I go V.H.pair.next, So this is, so we're just chasing a lot of errors here. v.h.pair.next. Then I get to the half edge that I want, and then this is at the tip of that half edge. All right. Now it's going to start to get a little bit tough to write. So maybe this is the last one I'm going to totally write out. But I'll just tell you, I'll just draw it for you. I mean, you just keep repeating this process. It's you know, you flip, next, tip. Flip, next, tip. Flip, next, tip. So let me do that again. So I'll flip. And then because this has V as a tip, I know that the next one will have it as a tail, which is exactly what I'm looking for. I'm looking for a half edge that has this as a tail. And then I know that at its tip, it's going to have one of my neighbors. So I did flip, next, tip. All right. Now I'm going to take that, and I'm going to do flip, next, tip. And then I'm going to do flip. And I threw in a quadrilateral, jazz this up a little bit. Next, so next takes me down here. Tip. And then flip. Next. And actually at this point, I'm finished because I just ended up back where I'm started. So this is actually a great example of an algorithm that's, so maybe I'll write it like this. This is a great example of an algorithm that benefits from a do-while loop. All right, so I'll write a little bit of pseudocode here. So let me say, so this is the method get neighbors, and I'll say, okay, h is equal to, you know, I'm going to start off, h is equal to v dot h, right? So what some arbitrary half edge that's coming out of this that has it as a tail. I'm also going to gather all of the neighbors into some kind of list. And so now what I'll do is I'll say, okay, do while something. So I'll finish that in a second, but what am I doing? Okay, I always take the vertex that's at the tip of the edge. So this h is like my cursor that's helping me to loop through different half edges. So I'll say nabs dot append h dot tip, and then I'll move h along. So I'll say h equals h dot pair dot next. That's the loop I do this whole time. And I'll do that as long as I haven't gotten back to where I started. So there's my do while loop. That expresses exactly what I said here. So start off at h. Start off with h at v.h. And go ahead and go to the tip, add it. And then do pair next. So here we are. Is that equal to v.h? No, so I'm going to keep going. I'm going to append that tip and then go pair next, so on and so forth, until I get back here. And this makes sure that I don't accidentally add the tip of this twice. Okay? So that's one of the tasks that you're going to have to do on the homework. I also ask you to get the attached faces of a vertex. So it's like all these faces that are coming out. And that's really quite a simple tweak to this. So if I wanted to get attached faces, well, I just have to change this to, instead of saying, okay, I'm going to append h.tip, I'm going to append h.face. Now there is one small caveat to this. If I were, for example, going to ask you of the neighbors of this vertex up here. So let's say I was going to do that. There's something kind of interesting that happens here. So let's say I happen to give you this half edge coming out of it. I could follow the same algorithm. So I can go, you know, okay, it's what's ever at the tip there. Then I'm going to flip to the other side. Now what's interesting here, when I flip to the other side, I'm actually on the other end of a boundary, right? So notice this edge only actually has one face on the other side of it. So the convention that I follow, which I think is a pretty reasonable convention, is that a half edge points to null if it happens to be on the other side of the boundary. Okay, so this is null. And also, okay, but then it still has a previous and a next. And so the previous and the next are actually along the boundary cycle. Right? So the half edges on the outside are the boundaries. And they just go ahead and they go along the boundary in the appropriate order so that the half edges on the other side are counterclockwise with respect to the faces, right? So I check that one there. That's going counterclockwise. I check that one there. It's going counterclockwise. So just to say, this points to this points to this. It's getting a little busy there, so I'll clean that up. And so just to say, the half edges along a boundary actually point you along the boundary loop. All right? And the face that they point to is null. So this algorithm for the vertices, for the vertex neighbors will still totally work. So I'll go, if I was looking for the neighbors of this vertex, it'd be these three, right? So I would this algorithm would still work. I would say, okay, start with this half edge. It's that tip. Then go pair next. Okay, it's that tip. Then go pair next. It's that tip. Then go pair next, and I'm back to where I started. So that works. Where I have to be a little bit careful is where I add the faces, because if I follow in the same traversal here, I would say, okay, first half edge, I'm going to add this face. Then I'm going to go to pair next, but the face is null here, right? So I don't want to actually add that face. This face is kind of like all of the outside. So I do not want to add a null face to my list of face. The code that you have will crash if you do that. So I'm just gonna say maybe add an if statement here. So I'll just make sure that I'll say if h.face is not null, then I'll add it. And I think that's all I need to do to clean this up. But otherwise, yeah, I still continue on looping like that. All right. So that's the basics of half edge and half edge traversal. So I hope this helps you out. And in the next video, I will just give a couple examples of how to do this programmatically. So we'll look at the code and I'll show you how to initialize some half edge examples.